Hi folks, we're going to take a look at the solution to page 570, number 18. Okay, so if we look at the question, it says the shadow cast by a man standing 1 meter from a lamppost is 1.2 meters long. So if the man is 1.8 meters tall, walks away from the lamppost at a speed of 120 meters per minute, at what rate is the shadow lengthening after 5 seconds? Okay, so let's start by drawing ourselves a diagram here. Okay, so this is a type of question that we've seen before. So we've got a lamppost. Okay, now they don't give me the height of the lamppost, but they do give me the height of the person walking. Okay, and let's see, that was 1.8 meters. Okay, and the lamppost is casting a shadow. And what we're looking for, okay, is how quickly the length of the shadow is increasing. Okay, so that's something that's changing as the man is walking. Okay, and in fact they tell us that the man is walking at 120 meters per minute. Okay, so I'll just get that down there. So we want to know how the length of the shadow is increasing as he's walking 120 meters a minute away from the wall. So that means that the length that's going to help me describe that is this is the length that's changing at 120 meters per minute. Okay, so let's call that x. And what I have to do is I have to find some relationship between these two variables so that I can use the rate of change of one to find the rate of change of the other. Okay, the only problem is in this diagram, and we've seen this problem before, is since there's no interest or information about the hypotenuse, it makes sense to work with similar triangles. Okay, but we need some other side on this larger triangle, because the only thing we have on the larger triangle is that x plus s is a side on it. So since I have the height of the man, would be good to have the height of its corresponding side, which is the lamppost. And this is where we have to look at the other information they're giving us. In fact, the information about the initial values. Okay, so at the beginning, what we have is we have some specific values. Is at the start. Okay, so if I just sort of redraw the scenario, at the start, okay, man is still 1.8 meters tall, but he starts 1 meter from the wall, and at that moment in time the shadow has a length of 1.2 meters. Okay, so what I can do is I can determine the height of the lamppost using this information. Okay, so that's what makes this problem a little trickier than the original one we saw that we solved, is we need to find some information first. So let's solve for that here. So if I take this side y over its corresponding side on the smaller triangle is just going to be 1.8, and that's going to be equal to the ratio of the bases. Okay, so the base on the larger triangle is 1 plus 1.2, so 2.2, over its corresponding side, which is 1.2. And so y is just equal to 1.8 times 2.2 divided by 1.2. Okay, so let's calculate that. Okay, so we've got 1.8 times 2.2 divided by 1.2. Ah, it's a nice number, 3.3. Okay, so y is equal to 3.3 meters. Okay, so now I'm going to add this in to my diagram here. Okay, so we know this is 3.3, and now we can solve this in the traditional way, which is again to use ratios, but with these changing components. Okay, so the way I'll write it here is I'm interested in the shadow, so I'll start with the small triangle. So this base S, okay, corresponds to the full base of the big triangle, which is x plus s, and that's going to be equal to the ratio of these two corresponding sides, 1.8 and 3.3. Okay, and there's a pretty easy equation to simplify here. So we've got 3.3s equals 1.8x plus 1.8s. Let's bring that to the other side. So 3.3, 4.3, 3.5, I guess, or sorry, I got that wrong. 3.3, 2.3, and then 1.5. Sorry about that. So we have 1.5s equals 1.8x, and this is a nice relationship between my two variables. So now what I'm going to do is I'm going to take, the derivative of both sides with respect to t, of course, since that's the rate I'm interested in. So 1.5 is just a constant, so I'm taking the derivative of s with respect to t, so s prime, I'll write it that way. 1.8 again is just a constant, and this is just derivative x with respect to t, which I'll write as x prime. Okay, and lo and behold, x prime is exactly that rate that I'm given. Okay, the rate at which this distance from the wall is increasing. Okay, now I want you to go back and notice that my original equation relating to the two variables was a linear one. So they actually asked me what the rate the shadow's lengthening after 5 seconds. I actually don't need to know the time or any other information since this relationship is linear. So again, they just gave us some extraneous information. So here, let's put in what we know. So 1.5, s prime is what I'm looking for, x prime is what I'm given, and so s prime is just 1.8 over 1.5 times 120. Okay, and so here, let's put that in here. So 1.8 divided by 1.5, okay, times 120 is 144. Okay, which is what I'm looking for. And here again, this is a length which is given in meters per unit time, which if we go back was in minutes. Okay, so just to recap, we set this up similar to the other shadow problem that we solved, except we were missing a piece of key information. So that's where I used these initial values to calculate the height of the lamppost, and then from there I was able to solve it my traditional way. Okay, that's it for this one.